You're not workshop, like a a week. Just like
Get started. The last people up there?
I'm sorry.
Are they allowed? I did ring the bell. Yeah.
All right. Welcome to day 4 of the workshop, and the theme today is quantum chemistry applications. I'll ask the speakers to repeat the questions as we've been doing, but I will also try and circulate the mic. So if you have a question, it'll show up on the recording. And our first speaker today is Martin Head-Gordon from UC Berkeley, and he's going to tell us about computational quantum chemistry, classical gaps, quantum opportunities, and open questions.
Okay, good morning, everybody, and thank you for coming. It's a pleasure to be here, and obviously, please ask your questions as we go along, if you like. No need to wait till the end. So I'm a theoretical chemist, I guess, which used to be a contradiction, but these days something like maybe 20% or so of researchers in chemistry departments do theoretical chemistry, which is basically simulations, and so my particular area of simulation is computational quantum chemistry, and so almost all of my expertise and effort goes on the classical side of this, and so the first part of this talk will really be a bit of a perspective on what has been achieved and what has not been achieved in classical quantum chemistry simulations to date, and what is sort of a little bit of perspective on the field, and then I'll go on to a bit about the potential for quantum simulations in the near term, and describe a couple of the projects that I've been involved in. These are collaboratively with Birgitta Whaley, my next door neighbor in Gilman Hall and chemistry department colleague. Our joint students, we have a quantum group that meets once a week, and also with Lin in the math department. Okay, so well, kind of fun to begin with just some words. So here are some words from a Nobel lecture. The era of computing chemists, when hundreds, if not thousands of chemists will go to the computing machine instead of the laboratory for increasingly many facets of chemical information, is already at hand. And that was in recognition of a Nobel Prize given to Robert S. Mulliken, a famous theoretical chemist from the University of Chicago in 1966. And in 1966, this was only roughly a decade, maybe 15 years after the president of IBM prognosticated that there was a market for maybe 5 computers in the world, and obviously that changed. In December of '66, Mulliken went on to say something like, the obstacle is that someone must pay for the computer time, because it was so expensive then. And in a sense, one of the interesting questions about quantum simulations in computational chemistry is what era do they map to in classical simulations? And there's quite a bit of analogy, I think, to the mid-1960s. So there is great excitement, great potential, and at the same time a kind of a cost gap and capability gaps. So anyway, so really in some sense today the question is this or that. How will we do the simulations of the future? And so that brings me to part 1, which in some sense is drawing on my core expertise. So this is really where I feel give you a useful perspective. So what are the classical capabilities and where are the gaps? What is density functional theory, which is used for about 95% of today's quantum chemistry calculations, of which the rate that they are run is probably on the order of millions of simulations per day. Then couple cluster theory, which is a higher end solution, higher polynomial scaling. DFT is not worse than cubic scaling. And then exact classical solvers. When are they needed, and what is their current capability? And just as sort of a punchline, because sometimes you should hear what you are going to hopefully take away before you get all the arguments. Really, the gaps are in classical simulations are achieving high accuracy, and we'll talk about what that means. For large systems, we'll talk about what that means. And especially strong correlations, and we'll talk about what that means. And anyway, so this will be part one. Okay, so just to put us on the same page, oh yes.
Just a quick question, so the techniques, like a couple cluster theory, these are all like approximations based on some ansatz you're going to choose, I suppose.
Yes.
The exact classical solvers.
Yes, so exact classical solvers, as we'll discuss in a moment, are exponential scaling in principle, and they're never really exact anyway. So they achieve exponential scaling, yes. Whether or not they achieve exactness is another question. So these widely used alternatives can be viewed as kind of reasonably well-defined families of approximations that are systematically improvable, that are straightforward to execute, that is, well-defined black box type methods, and they work 95% of the time as a kind of rough heuristic. They don't work with as much accuracy as one would like for big systems, so that's a deficiency. And then in something like 5% of cases, they actually break down, they really fail. Okay, so I hope I can leave you with some sense of what that actually means as we go on. Yep.
So why isn't there like a machine learning deep neural network thing? Like, what is the missing step?
Why is there not a machine learning deep neural network thing here? Well, that arguably fits in as downstream use of data that you might get from these sources. If you ask, where is ground truth to be found? Ground truth is to be found in the validated classical simulation methods. And then if the system is not large enough for your liking that you can reach with a cubic scaling method, well, you could then hopefully leverage the capabilities of DFT to achieve linear scaling. So, for example, the UMA model, the united model, the universal model for atoms that Meta's FAIR team released roughly a month ago, is trained in large measure on a density functional developed in my group that they ran 50 million odd times, that is on 50 million different instances, to develop a molecular data set that was supposed to be diverse enough that they could then capture the performance of that density functional, which they viewed as good enough to be worthy of running 50 million calculations, and then leverage it to larger systems. So I would say that machine learning and AI is not really a piece of this, but certainly machine learning is then an enabling technology to leverage the stuff you see here, but it won't transform it because ground truth is not available in abundant supply for the failure modes or the areas of limitation. Thanks. Alrighty. So anyway, yeah. So this is the electronic structure problem. So here is the Hamiltonian that describes chemical systems, and it contains kinetic energy, electron nuclear attraction. The nuclei are considered to be clamped in space. So in other words, I prescribe, or the user prescribes, a geometry for the molecule, so the capital RA are fixed, setting a background field. Then there is the electron-electron repulsion term, and that is what prevents separating this Hamiltonian. This is the two-electron term, and there's the trivial nuclear-nuclear repulsion term. So all people in my area have jobs thanks to this term, which makes it interesting. And it's an eigenvalue problem. So we are looking for the ground state, m equals 0, and m greater than 0 are excited states. the scale of electronic energies is much, much bigger than the scale of thermal energy. So if you consider that kT, Boltzmann's constant times temperature, 300 Kelvin, gives you an energy scale of something like 2 kilojoules per mole. The gap between E0 and E1 in molecules is more like on the order of 200 kilojoules per mole at a minimum, and sometimes more. So by and large, we are interested in the ground state unless photons are involved, unless photochemistry is involved. So we're after then the lowest eigenvalue of the time-independent Schrodinger equation, and the variables don't separate, and furthermore, there's a symmetry, or to be exact, an anti-symmetry requirement. We want eigenvectors to be anti-symmetric functions in interchanges of permutationally equivalent electron labels. So that then leads us naturally to many electron building blocks that are determinants because they change sign on interchange of rows or columns. And so determinants are the wave function, and then if you get the m equals 0 ground state, you can in principle walk on it because it defines a multivariable surface. If you've got 10 nuclei, it's a 30-dimensional surface, and molecules represent simply local minima on that surface. And chemical reactions are the pathways that connect one local minimum to another. And so in principle, solving the Schrodinger equation allows simulation of reaction mechanisms by then exploring the topology of the resulting potential energy surface. And as you would understand, if we simply discretize an n-dimensional wave function, the complexity of doing that will grow exponentially. So then the success of theoretical chemistry is development of a hierarchy of approximate models. And chemists and physicists have a surprisingly different viewpoint about these things. Often physicists will model the Hamiltonian, whereas theoretical chemists, we view this as handed to us on quantum mechanical tablets, and we don't touch it because after all, we want to simulate the real molecule, not something that is an idealized molecule. And then in contrast to some other fields, we actually solve our approximate models extremely precisely. And this at first sounds a bit silly. Why solve a rather approximate model very precisely? The reason is what we want to actually get out. And what we want to get out are the energy differences between different local minima, or a minimum and a saddle point. And the question is, what is the scale of the energy difference compared to the absolute energies? And the answer is, it's incredibly small. So it's very much similar to the sort of silly thought of wanting to weigh the captain of a ship, and instead of asking the captain to step onto some scales, instead you first weigh the ship, and then you weigh the ship and the captain, and then you subtract. And that is why we need high precision in order to do that subtraction carefully. Of the the chemical energy differences are on the order of tenths of a percent, if not smaller, maybe tenths to hundredths of a percent of the absolute energies. The absolute energies are dominated by the electrons that are closest to the nuclei, the core electrons, and they actually are relatively unaffected by chemical changes, but not completely unaffected. So we need to leave them in, and so this leads to a requirement. And so to also give you some sense, on a classical computer, we will typically try to converge the energy to as close as we can to full double precision. So maybe maybe about 10 to the minus 8 or 9 atomic units, the natural unit, the reduced units in which the electron mass is 1, and Planck's constant, h bar is 1, and so forth. So this is important, and thus models that have noise, significant amounts of noise in them, will prohibit you from doing this subtraction and getting a meaningful answer.
Sorry, so just to follow up on Umesh's question, I've often tried to extract an answer out of chemists, like if you can say anything about like relative scaling of the energy gap you're looking for, the precision relative to the size of the molecule or something, or should I always think of this as a constant size system somehow that it's not even meaningful to talk about?
Well, chemists like to talk about size-intensive quantities, and that would be the first limit. So for instance, if you want to measure a bond strength between a carbon and a hydrogen atom, well, that bond strength is roughly the same regardless of the size of the molecule. So in other words, if your chemistry happens to be something like combustion, where CH bonds must be broken, then you're going to be measuring energy changes that are roughly independent of the size of the molecule. It doesn't matter whether your fuel is acetylene, a 2-carbon molecule, or octane, an 8-carbon molecule, or diesel, something like 30, or even a solid. So that's one extreme limit. And so typically it is these size-intensive quantities that we want. So in principle, that leads to a distressing conclusion that the precision you need might actually have to increase as the size of the molecule gets bigger in order to make sure you get a significant answer.
How do you define size of molecule?
Counting atoms. Yeah. So in other words, if we think about hydrocarbons as a class of molecule that might be roughly CnH2n or CnHn, then we're just thinking about scaling n.
So relative to the size of that molecule, say like the scaling of the precision you want, if you have like n atoms, do you want precision like 1/n or something? Is that obvious? Or?
Well, we typically start off with, that is roughly right. In other words, the total energy is extensive in n. The energy difference we want is independent of n, typically. Yep, so that's right. And so at some point you might then, even on a classical computer, strike the notion that really you should be computing in quad precision rather than in double precision. But we don't typically strike that today. Yep, question in the back.
So you said that chemical reactions connect one minimum to another.
Yeah.
So how well do you know this is the case, and in particular, like what role is played by by the whole landscape? Like, can there be some equilibrium dynamics that is not just like one?
Oh yeah. I'm simplifying a lot here. So this is the zero temperature picture of chemistry, right? And of course, the room temperature picture of chemistry then brings in the sister field of statistical mechanics that is a sister to quantum chemistry, that is concerned with thermal fluctuations and how a system actually crosses a barrier, which is then a low probability event, by making repeated attempts. So at zero temperature, this is absolutely the rigorous picture. In other words, all dynamics is quenched, and you're really asking about zero velocity trajectories in a kind of high friction limit that take you, from one minimum over a saddle point down into another one.
Yeah, but I'm asking if the dynamics matter, so you only care about, let's say, the distribution of eigenvalues, and like even when you have thermal fluctuations, is that because like, can you have something like when you run Schrödinger equation, like there are quantum fluctuations, there is like the whole thing. Does that matter?
The quantum fluctuations typically don't matter because the energy scale of hopping, promoting from m equals 0 to m equals 1 is typically on the order of 100 kT or so. It just doesn't typically matter. There are exceptions, and of course, what I'm giving you here is kind of the typical cartoon, and there are exceptions where if there is an electronic near degeneracy, then you get interesting effects. So, for instance, temperature-dependent magnetism would be an example where near quantum degeneracies are playing a role. Yeah, thank you. All right, where was I? So this is then the overall picture, and now to try and give you a little bit of a sense of what is computational quantum chemistry today? Well, it's used by on the order of 100,000 or hundreds of thousands of researchers in academics, industry, government labs. There are dozens of software packages that implement the models that I'm going to describe. There are maybe 10 major ones, and so quite a lot of computer time is invested in this. And the code that my group works on is some 3 decades old. It's something like 10 million lines of code. It's distressing to say that, of course, no human being actually knows it all, so maintenance and evolution is difficult. There are some hundreds of contributors, maybe on the order of 400 or so cumulatively. So it's also teamwork. So in contrast maybe to Linux, or maybe it's a little like Linux, the community of developers is rather small compared to the community of users. The community of users wants a black box, basically, and they would like to unravel complex chemistry. Where are we here? Wrong button. And an example of that would be, this catalytic cycle here towards green chemistry, the kind of the PTA. This is a modified version of paraphthalic acid, and so then walking on these potential surfaces is going from reactants to products via various intermediates, and the kind of most interesting chemistry is catalytic, which is to say there's chaperones helping a chemical reaction along, and so there are many steps along the way, and a reaction mechanism is the sort of thing that this cartoon tries to capture and that the computations try to capture. And you can then see that you need the barrier heights, first energy, and then if possible, free energy, to enough accuracy that you can predict rates, turnover rates. And if you think about trying to compute quantities like barrier heights that go into the exponentials of kinetic theory, you would like high accuracy. And so this is heading towards one of the gaps of classical quantum chemistry, that we don't always deliver high enough accuracy to get the rate within a factor of 2 certainly, and 10 sometimes. So that sounds bad, but of course, it still translates to an error that is quite small. So high accuracy is a demanding thing because in the end you want thermodynamics and kinetics to be predicted correctly or modeled correctly. And 95% of the world's computations in quantum chemistry today are done by density functional theory, so I should tell you about what density functional theory is and what it's good for and what it's not so good for. And then, and in some sense, a mantra is that about 95% of chemistry is easy. That is not easy to do in the lab, not necessarily easy to compute, but in principle easy in the sense of being accessible to the models that have become popular, that have been highly developed. And to come back to the question asked earlier, DFT is increasingly the source of ground truth to train machine learning interaction potentials. Okay, and now to focus on a bit on the categories of models. So I gave you the quote from Mulliken, that was Nobel Prize 1966. There was another Nobel Prize for wave function theory in 1998. And the point here is that at least notionally, straw man style, notionally exponentially complicated unknown function is modeled in a way that replaces this beast by something simpler, and I will talk about coupled cluster theory as the most successful family of wave function approximations. And on the other hand, as I've already told you, it's the second most successful approach. Density functional theory is dominant today, largely because everything's a trade-off between accuracy and feasibility, and the feasibility of typical density functionals is considerably greater than the feasibility of typical coupled cluster models. And to just and of course in some sense you can get a hint of it by replacing the 3n dimensional wave function by a 3-dimensional electron density as the core variable. And then Hohenberg-Kohn, theorem number 1, says that the ground state energy can in principle be determined without knowledge of the wave function, which is great. Then the kind of density functional theory that is used today, Kohn-Sham density functional theory, actually reintroduces a one-determinant wave function that describes fictitious electrons, and it's dragged in to evaluate the kinetic energy for which no adequate density functional exists today. So Kohn-Sham theory uses orbitals, that is one determinant's worth of one electron functions that describe fictitious electrons whose density is exactly the same as the interacting electron's density, and that's used for the kinetic energy. And with that, the total density functional theory energy, I write in red here because you should view it with concern. You should view the total energy with concern, and the concern arises from only one term. 3 terms that are the biggest term, the second biggest term, and the third biggest term are exactly evaluated within Kohn-Sham DFT. The 4th biggest term, exchange and correlation, we don't have the exact functional, and in my opinion, it's unknowable in the sense of we can characterize it in various ways, but its exact form is absurdly complex as a functional of the electron density. So then what goes on in density functional theory is then making models to approximate the exchange correlation energy. And these models, if they are black box and well-defined, they represent density functional theory model chemistries that a chemist can use while knowing nothing other than the name of the functional, and then some sort of common knowledge about how good is the functional that you are thinking about using for the kind of problem that you hope to solve. Alrighty, so that's that, and let's then talk a little bit about how density functionals might be classified and how good, bad, or ugly are they. So the most useful classification is due to the great physicist John Purdue, and he suggested that that there is a metaphorical stairway to heaven, either a Jacob's ladder if you happen to have a biblical bent, or maybe if you're a Led Zeppelin fan, just a stairway to heaven, where you begin with the primordial ooze of simply setting the exchange correlation energy to 0. And if you do that, electrons don't have the correct spin statistics. The anti-symmetry associated with the Pauli principle is not adequately captured. So then you climb up to rung 1, which is a dependence on the density pointwise. So this is the rung 1 density functional form, which is an integral over the coordinates of an electron, r, and then an exchange correlation energy density at that point that depends on the density at that point. And this is obtained from the exact solution to the toy problem of a uniform electron gas. And it's an outrageous kind of expression because exchange and correlation, by their very definition, involve 2 electrons at a minimum. Yet this is a model that involves only 1 electron at a time. So you might, so again, that's why this was in red on the previous slide, to invite you to feel concern about this. But nonetheless, this functional is exact for the uniform electron gas, and so is the exact functional, which is unknown. So let's take this one that is known, that is exact for all uniform electron gases, and transfer it to non-uniform electron gases, like molecules. And so that's rung 1, and I'll show you data for rung 1 in a bit. Then rung 2 is to keep this so-called semi-local form, an integral over the coordinates of 1 electron, but allow it to be in principle exact if you design it very well for slowly varying electron gases by incorporating a density gradient dependence. And so this is called the local spin density approximation, LSDA. There are on the order of 24 examples of these generalized gradient approximations because there is no single unique way to do this. They come with cryptic-looking acronyms that typically represent the names of the physicists and chemists who developed them. The B is Axel Becker, who is Canada's greatest theoretical chemist. The P is the John Purdue already mentioned there. Then you can climb to rung 3, and in this classification, rung 3 introduces second-order information, so maybe that makes sense. And at some point, this becomes a losing game. There's nothing left to gain. And you need to ask, how do I introduce non-local information? How do I introduce information that depends on 2 electron coordinates at once? And that comes at these rung 4 and 5 of this ladder. And so rung 4 introduces a dependence on the occupied orbitals of the cone-sham determinant, and that is then wave function exchange. So that can no longer be written as an integral over the coordinates of 1 electron. It's an integral over the coordinates of 2 electrons. And there are many, many examples of this. This rung is where most of my group's work on functionals has been centered. And then rung 5, as you approach the heaven, is a dependence not just on the orbitals that are occupied in the cone-sham determinant, but a dependence on the orbitals that are empty. And at this point, you have really hybridized density functional theory and wave function theory. But anyway, this is a sort of a way to think about density functional theory that is useful for both experts and newcomers. Yes?
So the rungs of this ladder, the development of the rungs of this ladder are not monotonic in time.
No.
So what was the purpose of developing rung 3 if...
Well, I guess technically the rung 2 and rung 3 were anticipated in 1966. However, nothing useful was done until the mid-1980s in this case and the late 1990s in that case. And so the rung is, the date that I've attached there is my personal view of when it first became useful, rather than when it was a sort of dream in the mind's eye of someone. So anyone can imagine local expansions, but translating it into something that actually proved useful, and in fact really was responsible for the 1998 Nobel Prize. It developed in the mid-'80s, and so the 1998 Nobel Prize was a consequence of that translation of an idea that always seemed like it had potential.
And just to follow up on that, so is the primary reason to pursue one of the lower rungs just that it's computationally cheaper?
Well, let's see. So there's the lowest. Well, there are many ways to think about that, but in principle, the computational cost gap between rungs 1, 2, and 3 is very small. So if there is a rung 3 functional that dramatically outperforms rung 1, and I'll show you data in a minute, then there is no reason to use rung 1 at all. However, there is a significant cost gap jumping up to rung 4, although it's an active area of research to look into, is that necessarily true, or is that just because our algorithms for evaluating exact exchange have not yet evolved to the highest possible state of perfection? And then it should make sense that a rung 5 functional, which depends on empty orbitals, could be qualitatively more costly. Even arbitrarily costly. It could be exponential, and this rung presumably definitionally contains the exact functional finally. And we know that one is likely to be exponentially expensive. Thanks for the question. Yes?
How do you certify the accuracy of any of these methods?
Great question. There are so the question, I'm sorry, I'm doing a terrible job of failing to repeat the question. The question is, how does one certify the accuracy of any of these functionals? And there are 2 ways you could think about it. One is with respect to data, obviously, and so I'll show you that on the next slide. And one thing that I haven't put a slide on, but I could have, is with respect to the known exact conditions that the exact functional must obey. how many of those are obeyed. And I already told you this obeys one condition the exact functional must obey, which is exactness for the uniform electron gas. It's interesting that until you get to rung 4, nothing is actually exact for one electron systems, which obviously the exact functional should be exact for. And until you get to rung 5, nothing has the possibility of being exact for 2 electron systems. So exact conditions and data. All right, so speaking of data, this is now going to be a jump into a roughly 5,000 data point database that was assembled here at Berkeley in my group by Nabe Marderosian, a brilliant student. And we group the data points into a bunch of categories that mean something to chemists. It will take too long to explain all of the categories. Let's just pick on barrier heights, because I talked about the pathway connecting a minimum to a saddle point as a reaction path. So if you look in this column, this is the 1 sigma error. So in other words, if you like high quality, you should think 3 sigma. In chemists' units, which are kilocalories per mole, if you want to convert that to kilojoules per mole, multiply by 4.6, by 4 roughly, and then multiply by 25 to convert it into electron volts. And a typical reaction barrier might be anywhere between 5 and 50 kilocalories per mole. So this is more or less useless. So that's the first thing to say, and therefore it's shaded deep red, and we're heading towards something that is deep green as high quality. And so if we then go to the GGAs, their value is evident in a twofold narrowing of the error distribution for barrier heights. And this, in a statistical sense, is an answer to the data validation question. You might ask, how much accuracy does a chemist actually want? Remember the high accuracy need? It is a minimum of 10 times better than this. So this is not accurate enough for our aspirations by any means. And this was relatively useless, but this narrowing of the gap is important. So this is, by the way, the result of assessing over 200 existing density functionals and taking the best one at each rung to then show you, well, how do things improve as you add what essentially amounts to more flexibility in the functional design. And so you can see another twofold reduction roughly here for the best meta GGA, the best rung 3 functional that has second order information in it. And then at rung 4, roughly another twofold improvement. And we don't know, by the way, whether we have yet discovered the best functional at this level or that level. It's very likely we are very, very close at this level because this is such a simple form, and this one is fixed by its model system. And then this one is, of course, the best functional at this rung will have an RMS error of 0, but this is a tractable functional that lives at that rung. And so this is still not accurate enough. So a chemist would typically tell you that DFT is not chemically accurate, but at rung 2 and better is good enough to be useful. So that's kind of a quick bird's eye data-driven view of what is the status of density functionals today. Yep.
So DFT is also used to model materials. So for industries, what rung would be sufficient?
Well, again, one would like to be on rung 5. And today, in the modeling of materials, it is most common to use rung 2 or rung 3, and there is rapid progress being made in materials modeling at rung 4. And in fact, in collaboration with Lin and I have a joint student working on rung 4 for solids. But yeah.
Sorry, but the chemical accuracy there is not necessary. What is the required accuracy there? Is the same one?
Well, again, if you are doing reactions that involve, for instance, a molecule on a surface, the accuracy requirements exactly the same. If you're interested in the properties of a bulk material, it's more forgiving. In fact, the first useful applications of the LSDA were to solids for band structure. Yep. Yep.
Here, I guess we use this different functions to get energy, but do these functions actually tell you more about sort of this molecules it's like is it for other things?
Yes, once you have specified a functional, you get access to the energy. And in principle, any property, any molecular property is accessible once you get the energy. So molecular properties, things that characterize the molecule, are all energy derivable. So for instance, the electron density is the response of the energy to a delta function perturbation at point R. Or the dipole moment of a molecule is the response of the energy to an electric field perturbation, or and so on and so forth. And then you get the structure by minimizing the forces to zero. So you get access to everything. Spectroscopy is then higher derivatives. So in principle, everything is, almost everything is known. There are a few things that the theorems of density functional theory say you cannot access. So you can't get access to some kinds of properties of two electron operators because they are not connected to the ground state energy, but very few things. Yes.
So I'm hoping this is a reasonable time to ask this question. So a few slides back, you had a chart with energy and free energy.
Yep.
I was wondering if you could just sort of elaborate what is the difference, which one is the important?
Right. So free energy is formed as the enthalpy plus T times the entropy, and that's the thing that is of most direct relevance to a practicing chemist, because free energies determine whether a reaction is spontaneous or not, and they also determine the turnover rates. The energy itself is the most important ingredient in the free energy. And then the second most important one is the entropy, and that is associated with thermal fluctuations in the nuclei, and so you can either. So when I showed you G in that slide early on, that was being computed from a model partition function associated with the harmonic oscillator. So in other words, assuming the nuclei are vibrating in parabolic potentials. Because you get access to that directly from, once you've minimized a geometry, you can then compute the curvature for displacements of all of your 3A nuclear degrees of freedom. It is a problem in statistical mechanics to properly compute the free energy. And so that G that I showed you in the catalytic cycle was a model free energy. Well-defined, but not exactly nature's. Thanks for the question. Yes?
So what are these numbers?
These are the 1 sigma errors, so they are root mean square deviations against ground truth to assess these approximate density functionals. So thank you for asking. The ground truth you might first think should be experiment, but that is actually much too difficult. So in fact, the ground truth is coupled cluster theory, which I'll tell you about next, which is how you go to higher accuracy. But yeah, so given ground truth that is hopefully at least 10 times better than these errors that we're reporting here, that's the significance of the numbers. All right. So then, in terms of exact conditions, there's no guarantee. In fact, the functional here may satisfy fewer exact conditions than this functional or that functional. So then it's interesting to just ask, how well do they work? And so, in a statistical sense, DFT is systematically improvable, but not to the level of accuracy that we might desire. So again, when one kind of thinks about the gaps in classical quantum chemistry calculations in DFT, there is an accuracy gap on the one hand, and then the D category here is for difficult. difficult versus easy was decided by the people who developed the database. I'm one of them, so you can ask me about it. And that difficult is defined with respect to the failure modes of DFT. So if I compare thermochemistry easy to thermochemistry difficult, I see a gap that reflects a breakdown mode of density functional theory. And we want to know how bad are the results in difficult cases, as well as how good are the results in easy cases. And you can see a significant difference. And we don't know that we've included the world's most difficult cases here, but we've certainly got some selection. Okay, anyway, I could spend more time on it, but I think I want to just sum up and say, on the good side, you can see systematic improvement. You can also do big molecules, but it's not chemically accurate. And so if a quantum simulation can produce higher accuracy, that's of great interest. But it also has to be feasible enough to apply to big molecules. All right, and if it is okay, I will then move on to telling you about wave function methods, but after any final DFT questions like yours.
Is there a molecule or another example where DFT completely breaks down?
Yes. Yes, there are interesting examples. If you would like to see a really nasty breakdown that is nonetheless for a very simple system, the one electron system that is H2 plus is classic. And if one was to plot the energy as a function of the distance between the two hydrogen atoms, then the exact curve should give you a well-defined structure and go to a zero that is the energy. The zero here would be the energy of a hydrogen atom and the energy of a free proton, which is just zero. However, a density functional on rung 2, for instance, looks something like the following. It tracks very well up until a certain point and then does something like this. And in fact, it then breaks down by making two hydrogen 1/2 pluses instead of a proton and a hydrogen atom. And in principle, the superposition of degenerate states says this should be the same energy as that, but with an approximate density functional, it is not. And so that is a qualitatively incorrect prediction. And this is a defect of the exchange functional. All you need is an exchange functional that's exact for one electron systems to get this right. But this curve, in my mind's eye, I am thinking this is a GGA, that is rung 2. And trying to fix this up is a great reason to go to the hybrid functionals, which will look something more like the following. They don't fully solve it, but this would be a rung 4 functional, which has some exact exchange. If you had 100% exact exchange and you neglected the correlation energy, you'd be on this curve. That actually damages other things that you want to get right. So yeah, the breakdowns of DFT will be either breakdowns of the exchange functional, which manifest in systems with as few as one electron, or breakdowns of the correlation functional, which obviously take at least 2 electrons to manifest. Thank you for the question. That's an important one. And so in kind of sum, one would say that systems with odd electrons or odd holes may be vulnerable to this delocalization error, as it's called, which is a defect of the exchange functional. And the strong correlation class of problems, which is probably the best opportunity for quantum information, is will manifest in failures of the correlation functional. Yeah. Okay. Any other questions about DFT? Well, let's now switch gears to the other part of the classical family tree. So this is then wave function approximations to Schrödinger chemistry. polynomial scaling wave function approximations. Everything begins by doing mean field theory, which is then variationally minimizing the energy associated with a single determinant. So that is, of course, not Kohn-Sham theory, because now we're evaluating the matrix elements properly. And then do coupled cluster theory to approximate the correlation problem. And then I just want to remind you that we make a many-body approximation. What density functional do we choose, or what coupled cluster model do we use? And then we always work in an incomplete one-particle basis. So this is what I mean by saying that even the exact classical solvers are not exact, because they don't work in a complete basis set. In fact, they work in a truncated basis set. We know a lot about how things converge as a function of the size of the basis set, but to just give you an idea, anywhere between 20 and 50 functions per atom is what is typical, and that then leaves something like 10 to 20% of the energy levels that you get in mean field theory occupied, and the rest empty or virtual. And by making fluctuations from the occupied mean field levels into the empty ones, you will then describe what is missing in mean field theory. And so on the wave function side, the kind of mantra is to try to get the right answer for the right reason, by having systematically improvable polynomial scaling approximations. And so the basics of coupled cluster theory are, firstly, the choice of the wave function, which is nonlinear. So in other words, instead of a linear superposition, we take the exponential of a sum of substitution operators. So altogether, this thing you could look at as a correlation factor that dresses a mean field wave function to make it exact. And it becomes exact if you include substitutions all the way up to the number of electrons in your system. At that point, of course, the cost must be similar to an exact superposition of substitutions. So you don't want to do that. You want to truncate. So the important thing about truncation is that you get good results when you truncate at a finite level of substitution. So instead of allowing clusters of up to all electrons to fluctuate out of their mean field levels, stop at pairs of electrons, for instance. So that defines a theory that is called coupled cluster with singles and doubles, which is evidently exact for one electron systems, exact for two electron systems, and it is size consistent in the sense that it's also exact for an ensemble of two electron systems. And its compute scaling is polynomial, and naively it's order a to the sixth, although there is a lot of work reducing this to order a to the 1 with elaborate numerical linear algebra approaches. So, yeah. Oh, A is the number of atoms. So again, just thinking about homologous systems. So you could next go to truncate at T3, that defines CCSDT, or T4, that defines CCSDTQ, and these have steeper polynomial, but still polynomial scalings. And in principle, these can also be reduced to order a to the 1 if you are able to reveal spatial locality. So here is a family of models that we don't have a Jacob's ladder, but there's instead a truncation of T ladder. And this is very, very well defined, very clean. And so these are good models. And how do we solve them? To variationally evaluate the coupled cluster energy, even after truncation, is intractable, because the matrix elements only terminate at n-fold substitutions. So we can't do that, or we don't want to do it. So instead, the coupled cluster equations amount to solving the Schrodinger equation in a subspace. So just solve inside a subspace. And do that by projecting with, firstly, the reference function That's the Hartree-Fock determinant, p equals 0 in the notation of this equation. And then all of the retained substitutions in the truncated t, which defines a set of p greater than 0. And so this is h minus e psi is equal to 0 in the subspace of the reference and the retained substitutions. So that's then a closed set of nonlinear equations that yield the amplitudes hidden in the correlation factor and the energy itself. And you get polynomial scaling for any truncation of t short of going all the way up to complete system size. And the price for this subspace solution is that there's no variational bound on the energy. So the energy, instead of being guaranteed to be too high when you truncate, may be too low. And because we solve a subspace Schrodinger equation, the results are best when the reference determinant is really the dominant part of the wave function. And this could be viewed as a definition of weak correlations when the mean field wave function is the dominant part of the true wave function. Doesn't mean that it's 99% of the true wave function, just means that its contribution is big compared to any other determinant that you might like to pick. So weak correlations are when coupled cluster theory shines, and the opposite is the regime of strong correlations, where everything that I will now have told you today is on shaky ground. So we're eventually heading towards the 5% of problems that are really difficult. Okay, so coupled cluster theory. A picture is worth 1,000 words. So this is a beautiful picture from a beautiful article, citations down there. There are two axes here. The y-axis is walking up in truncation of the cluster operator, and the x-axis is expanding the size of the one-particle basis set. These acronyms mean something to theoretical chemists about increased angular momentum in the basis set. And the pictures are cartoons of the Gaussian error distribution associated with a small set of atomization energies relative to the very, very best that can be evaluated. And so you could then say, well, if I want to explore CCSD, I could then look at the convergence with respect to basis set and see a gradual narrowing of the distribution, but it's still a very broad distribution. Then if I fix the basis set at something small and I increase the cluster truncation, I can see a very nice narrowing of the red distribution. But then as I go up higher again, from triple to quadruple truncation, I see no change. So at this point, this set of data is dominated by errors associated with truncating the one-particle basis set, and you have to go towards the the upper right-hand side of this diagram to then produce beautifully sharp distributions whose accuracy is much higher than you can achieve with density functional theory.
What's the main source of error distribution? What's the randomness here?
There are two sources of error. One is an incomplete one-particle basis expansion. So that's the finite basis approximation reflected by going left to right. And the other source of error is the incomplete correlation description, or the incomplete n-electron description, which is truncating the cluster expansion, doubles, triples, quadruples.
I think the question was within a picture, what accounts for the variation? Are you looking at different?
Sorry. Yeah. This is the data whose error distribution is being shown here is a set of atomization energies. So this is taking on the order of a dozen, maybe 15 molecules and fragmenting them into atoms. And that's then a proxy for reactive chemistry. In other words, if I take the water molecule and I strip off its two hydrogens to leave two hydrogen atoms and an oxygen atom, that will be one of these data points. And then there will be a bunch of other very small molecules, because we're now doing more expensive methods. And what you're seeing then is the scatter in the resulting atomization energy. But it's the theme of this plot is look how beautifully things sharpen up as you go towards the x-axis limit and the y-axis limit simultaneously. This is showing you that these models have errors under very, very good control, that they are systematically improvable, that they are getting, when they get the right answer, they are getting the right answer for the right reason, which might be the thing that is not immediately evident in density functional theory, where you make models whose approximations are harder to trace. In DFT terms, exchange is exact always here. There is no such thing as an exchange error. We're just left with the correlation error and an incomplete one particle basis error. Okay, in that case, let me summarize. So great results, but too costly for large molecules. And a breakdown under strong correlation. And so the last thing I wanted, I guess I'm going to actually really give you only half my talk. Strong versus weak correlations then is the point to wrap up with. So in the helium atom, you've got 2 electrons, and if you think back to your general chemistry, the electrons are paired. And you've got 2 electrons in a 1s orbital, and to jump from the 1s orbital into any other level costs so much energy that the amplitude in the wave function of any configuration other than the Hartree-Fock one is very tiny. And so this is the regime that I've been really telling you about, the 95% regime. DFT and couple cluster theory work. And then the other regime, the interesting regime, most interesting regime from the point of view of quantum information, is when the correlations are not weak, but are strong. And this is typically in reactive molecules. In other words, if you want to take 2 electrons in the 1s orbital and get them to unpair, well, in helium, the only way you can do it is to make an excited state. But if you take those 2 electrons and you do some nuclear unfusion and turn the helium into 2 hydrogens, and then pull the hydrogens apart, well, eventually the electrons separate or unpair. And so there must be a process of unpairing as you go from the helium-like limit to the 2 hydrogen-like limit. And at the unpaired limit, 1sa and 1sb, well, 1sa could have a spin up, in which case 1sb should have a spin down, or the opposite. So there are clearly 2 configurations that are just as important in this limit. And that's a toy example just to get you thinking about it, but the definition of strong correlation is that in typically reactive molecules, the Hartree-Fock or mean field configuration does not stand alone, but instead there is an essential role for multiple configurations, and we're thinking of that, we typically think of that as a near degeneracy effect. And it's important not just for the high accuracy that we were talking about, it's important for even being qualitatively right. And there are complex systems, transition metal containing systems, that exhibit this kind of feature. And here, the kind of standard methods of classical computational quantum chemistry do not work. It's not just a question of asking for higher accuracy, it's a question of asking for a reasonable answer. There are some workarounds, there are some things that we do because this is very much a terrain that lots of people have looked at, but it's tricky. And so the standard solvers, well, they'll scale exponentially. We drop the nonlinear cluster expansion in favor of a straight linear Schrödinger solver. The exponential upper limit today is something like 20 electrons in 20 orbitals. When I say it describes strong correlations, that then comes with the asterisk that says to get the good answers, you need the weak correlations as well. And there's been a lot of effort to soften the hard exponential wall that lets you go up to maybe 60 electrons in 60 orbitals. And this is a slide from collaboration between Birgitta's group and my group back in 2020, pushing the exponential wall back. But to summarize, there's been roughly 60 years of classical quantum chemistry. We've got well-tested black box method. The workhorse is DFT. It's super cost effective, not highly accurate. And then coupled cluster theory classical coupled cluster theory is the high cost, relatively high cost, still polynomial, but higher scaling, high accuracy alternative. And then the challenges are about rate of convergence and versus increase in cost of computation. And the opportunity is in strong correlation that has this exponential scaling challenge. It's, in terms of open questions, it is not fully clear to me whether the strong correlation problem cannot be polynomially solved on a classical computer. It's just that it hasn't been adequately done so yet. So there's a lot of classical effort to seek novel approximations, and this is the fertile ground for quantum information. And you guys have asked so many great questions that I had a whole second part of the talk that I will spare you.
Though, maybe 10 minutes or so. Can you give us a preview?
I'll skip a lot of. Well, maybe what I'll do is.
Yeah. Or should we just back on?
Well.
No, we could get a preview.
Okay, let's go preview.
Okay, we'll do a quick preview. So, we're approaching the regime of 30 to 100 logical qubits coming online, and questions that probably you are all asking yourself, and to the extent that I play in this space, which is really in collaboration with Birgitta and with Lynn, the questions I'm asking myself are what kinds of proof of concept or early scaling tests are interesting, what kinds of promising algorithms could be there, and in some sense a punchline, I think, is that I think strong correlations coupled with weak correlations via hybrid quantum classical methods seems to be a very productive way forwards. And it's useful to maybe note, I'm going to skip a whole lot of stuff to show you one thing that, okay. What I want to kind of finish with is, the kind of there are some very interesting challenges that are unmet. And so if you kind of want to think, what are the grand challenge applications? This is one that Birgitta and I and Wendy, who I see sitting back there, and others thought a lot about in writing a proposal in February for an ARPA-E call, and it's about the oxygen evolving complex, which sits inside a protein. So this is a ribbon picture of the photosystem 2. And if you zero into the purple dot, there is then molecular detail hidden inside this. So this is essentially a giant molecule that lives in a cellular environment. And at its core is some metal atoms, manganese, and water, and oxygens, and calcium. And there are strong correlations in this complex. And the strong correlations arise because that complex is the catalyst for a water splitting cycle. The water splitting that happens in photosystem 2 is to take water, produce oxygen. This is, of course, what green plants are doing for us. And this is something that has strong correlations, weak correlations, a complex fluctuating environment, and is thoroughly beyond the reach of accurate simulations. So it's kind of the multi-scale challenge that one might think about as maybe something that these next generation of quantum devices could potentially help us simulate the thing we can't do well classically, which is the core, and if we can embed it, couple it to its local environment and to the long-range fluctuations, that is presumably the key to trying to model it. So anyway, I'll leave this as just a sort of an aspiration, I guess.
So if you were to give a 2-minute explanation of why, what your proposal is, what would that look like? And how would you tackle such a thing at a high level?
Well, at a kind of reductionist level, we find ourselves staring at the purple dot, and we then need to make a molecular fragment out of this. And it is a fact that chemists have done this already and have satisfied themselves that DFT doesn't work and they can't afford to do coupled cluster theory at the moment. And so in principle, a quantum solver for this molecular fragment could be imagined. as something that might be efficient, provided it is using a more or less an embedded Hamiltonian that takes account of the environment, which would have to be treated at a on classical computing. But the environment has no strong correlations, so the classical methods that I was telling you about work for the environment, but they don't work for the active site. And then finally, linking it all to statistical mechanics to look at the fluctuations of the protein that gate the transport of water, oxygen, and the electrons that are produced. You can then imagine a full simulation. We don't know the best ways to do the embedding of an active fragment into a classical environment for a high accuracy solver, but there are proposals, downfolded Hamiltonians or coupled Hamiltonians, and what did I have here? So essentially, I had a little bit the idea that you could have this as an embedded quantum problem, and so there's an active region that's actually quite small that you could imagine trying to solve on a quantum device, coupled to a quantum mechanical region that is treated classically on a CPU or GPU. And then finally, a protein environment, and protein simulators know how to do this with molecular mechanics or even MLIPs. And so that is in principle possible, maybe with on the order of 100 to 200 logical qubits. And we had estimates that the number of C-naughts for each ansatz state, well, this would be each determinant that we are going to use as a reference state in this strongly correlated core. That would be what we could think about. And so largely that's the sneak preview at any rate. And really, of course, the answer is I don't really know how to do it today. And part of that is because I'm not really a QIS specialist. I'm a QIS collaborator and participant. I know a lot about strong correlation on the classical side, and collaborating with Brigitte and Lynn is very interesting to think about, to what extent can we translate some of these ideas maybe to or fro. In other words, we don't know what is the best way classically to treat strong correlations, and I think there are some grounds for believing that polynomial scaling solutions classically could still be found that don't exist today. Anyway, so it's a fun area because it's a frontier. It's interesting in classical quantum chemistry that we are very much always benchmarking, and we set the goal as sort of black box methods that a non-specialist can use, and aspirationally we hope new black box methods emerge from the excitement in the QIS community about contributing to this application. Okay.
All right, maybe we'll save questions offline and resume here at 10 after. Okay.
In a way we can understand.